Okay, let's dive into this. Welcome to today's explainer, where we're tackling the complete blueprint of a complete blood count, or CBC. But listen, we aren't just going to stare at boring numbers on a spreadsheet today. No way. We're going to use a frankly brilliant framework known as the sponge analogy to translate those abstract hematology indices into physical, easy-to-visualize objects. It is a total game changer for how you understand the blood pumping through your veins.
To build this bucket piece by piece, here is our structural blueprint. Number 1, the setup and plasma. 2, red blood cells as sponges. 3, the factory floor. 4, the security team and patch kits. And finally 5, artifacts versus reality.
All right, part 1, the setup and plasma. So the crucial point here is establishing our foundational environment. Imagine the bloodstream is a bucket of water. Inside are sponges, a security team, and tiny repair kits. That water itself, that represents the plasma. Now, a CBC doesn't actually measure plasma directly, right? But it heavily impacts the results. Think about it. If the bucket loses water, say through dehydration, it might look like you have way too many sponges. But in reality, the ratio is just skewed because the water level dropped. Okay, moving to part 2, the sponges, or your red blood cells. Now that we've got our bucket filled with water, let's look at the actual sponges floating in it. Red blood cells are literally cellular sponges. Their entire job is to soak up oxygen in the lungs and squeeze it out into the tissues. A healthy sponge absolutely must be able to fold and squish itself through tiny capillary vessels without tearing. So when you look at an RBC count, you are simply looking at the total sponges in the bucket. Hemoglobin, or HGB, that is the absorbent material inside. It's the protein that physically grabs the oxygen. And Hematocrit, or HCT, is just the percentage of bucket volume taken by sponges. Like, if you pushed all the sponges to the bottom of the bucket, how much space do they take up? Usually it's about 35 to 50%.
Let's break down the physical traits of these sponges, starting with mean corpuscular volume, or MCV. This simply tells you the average size of your sponges. That's it, just the size.
Next up, we have mean corpuscular hemoglobin, or MCH. This is the absolute weight, or amount of absorbent material, inside a single average sponge.
And finally, mean corpuscular hemoglobin concentration, or MCHC. This represents the density of how packed your sponges are with absorbent material. And this brilliantly illustrates a key insight. A giant sponge naturally holds more total material, right? So its MCH will be high. But because the sponge is larger, the density of that material might actually be perfectly normal, keeping the MCHC normal. Because of that, MCHC is always a more reliable indicator of true hypochromia.
So when you put these indices together, you get these really clear clinical pictures. High MCV, or macrocytic, means giant, swollen sponges. Low MCV, or microcytic, means tiny, underdeveloped sponges. And a low MCHC, or hypochromic, gives you pale, flimsy sponges that just can't hold much oxygen. Now, if MCV tells you the average size, red cell distribution width, or RDW, tells you how uniform your sponges are. Do you have an identical set or a wild mix? A high RDW means there's a massive variation in sponge size. Clinically, this happens during regenerative anemia. If sponges are being actively destroyed, the bone marrow basically panics. It just dumps large, immature sponges, known as reticulocytes, into the bloodstream before they even have a chance to shrink down to normal size. And that idea of bone marrow panic leads us perfectly into section 3, the factory floor, where we'll look at the different types of anemia. Let's start with iron deficiency anemia. This is a material shortage. The factory is open, but the supply chain is completely broken. You've run out of the raw absorbent material iron needed to manufacture hemoglobin. The factory tries to do its best, churning out tiny, flimsy sponges just to get something into the water. So your CBC signature is low MCV and low MCHC, meaning tiny, pale sponges. You'll also see low reticulocytes because the factory isn't pushing out fresh replacements, it literally lacks the materials. The treatment? Iron sucrose to restock the warehouse. Once the raw materials arrive, the factory automatically resumes making normal sponges. But what if the factory is working perfectly, but the sponges are being destroyed once they hit the bucket? Well, that's regenerative anemia. The factory hits panic mode, dumping massive, raw sponges straight into the water.
Your CBC signature here is a high RDW because you have a chaotic mix of old normal sponges and massive new reticulocytes. You get a high MCV because those giant reticulocytes drag the average size up, and you get a low MCHC because they contain unfinished material that hasn't fully condensed yet. This usually happens in one of two ways. First, a Trojan horse situation, like a Babesia parasite invading the sponges and blowing them up from the inside. For that, you need an antiparasitic. Giving immunosuppressants would be a total disaster. The second scenario, rogue security guards, like an immune-mediated hemolytic anemia or IMHA. Your own security team mistakenly tags perfectly healthy sponges as invaders and hunts them down. That is when you use immunosuppressants, to drug those rogue guards and stop the attack.
Then we have non-regenerative anemia. This is a complete factory shutdown. The bucket has water, there's no active destruction, and the warehouse is completely stocked with iron. But the factory workers, they've gone on strike due to bone marrow damage, toxins, or a lack of hormonal work orders like erythropoietin. So the CBC signature shows normal MCV and normal MCHC. The sponges floating in the bucket are perfectly normal in size and color. There just aren't enough of them. That gives you a low RBC count. Iron sucrose won't do anything here, and immunosuppressants won't help either. You literally have to address the root cause of the factory shutdown, like managing chronic kidney disease or giving synthetic erythropoietin.
Okay, Section 4, the security team and patch kits. We've covered the sponges, so let's check out the active defense force and repair units floating alongside them. Let's look at the breakdown of our active defense force, the white blood cells. These aren't sponges. They actively patrol the water. Your WBC total is just your head count. A high count means an alarm was tripped, and reinforcements are being manufactured. But the differential? That reveals their specific roles. Neutrophils are your first responders for bacteria. Lymphocytes act as intelligence officers, like B and T cells, creating targeted antibodies. Eosinophils and basionophils, they are your hazmat team, handling parasites or allergic reactions. And finally, monocytes are the heavy-duty cleanup crew, eating dead cells and debris, like burst sponge fragments from a Babesia attack. Right alongside the security team, we have the patch kits, your platelets. Platelets are tiny floating tubes of glue that swarm and plug leaks in the bucket. Your platelet count tells you how many patch kits you have in reserve. Mean platelet volume, or MPV, is the physical size of the patch kits. A high MPV means the factory is pushing out large, fresh mega patch kits to keep up with active bleeding. Platelet distribution width, or PDW, indicates the size variety, like do you have a wide mix of tiny old patch kits and giant new ones? And finally, platelet crit, or PCT, asks if you swept all those patch kits to the bottom, what percentage of the total water volume would they take up? It's basically the total physical clotting mass available.
Which brings us to our final section, number 5, artifacts versus reality. We've got this perfectly assembled bucket analogy, but what happens when the machines looking at the bucket actually make a mistake? Seriously, what happens when the machine is just wrong? Automated analyzers categorize particles blindly by size and laser scatter. They have no context, and that lack of awareness leads to some very common, very dangerous machine errors. One error is the biologically impossible MCHC. Sponges can only pack so much material before they crystallize and rupture. It's a physical limit. So if a machine reads an abnormally high MCHC, it is almost always an artifact. This is usually inflated by hemolysis, where red cells burst in the tube during the blood draw, spilling hemoglobin into the plasma. The machine reads that free-floating material and artificially inflates the MCHC. It can also be inflated by lipemia, where high fats in the blood scatter the analyzer's laser, mimicking the density of hemoglobin. Then there is the hemolysis trap. During severe hemolytic disease, the factory prematurely releases nucleated red blood cells, or NRBCs. Analyzers will strip away the cytoplasm to count the nuclei, assuming that only white blood cells have them. So the machine falsely counts red cell nuclei as lymphocytes. It creates a falsely elevated white blood cell count while actively masking the severity of the anemia. It's a huge trap. Another classic issue is platelet clumping. If a blood draw is a little rough, highly reactive platelets can stick together in giant clumps. The machine completely misses the individual platelets, reporting dangerously low counts, and it might even misidentify that giant clump as a single white blood cell, which falsely elevates your WBC count. We also have to watch out for red blood cell autoagglutination. Severe immune diseases can cause red blood cells to stick together like clusters of grapes. The analyzer reads that massive cluster of normal-sized cells as one single gigantic red blood cell.
So the printout shows an impossibly high MCV and a falsely low total RBC count.
And this brings us to the ultimate failsafe. Every automated flag, every biologically impossible index, or sudden drastic shift requires reviewing a peripheral blood smear under a microscope. An analyzer can only read size and scatter. Only a human eye can reliably spot clumped platelets, nucleated red cells, or parasites. So the next time you're handed a spreadsheet of automated data, ask yourself this. Are you willing to blindly trust a laser, or are you actually going to look at the water in the bucket? Thanks for joining me on this explainer, and keep learning.